I think we should start.
Record.
All right, everyone, welcome to the RAR colloquium. And I'm sorry about the confusion with the...
Welcome everybody to another edition of the RAR.
Very sorry about the confusion with the link. That was totally screwed up on my part, but I sent a new link by email just now, so hopefully people have got it. So our speaker today is Dr. Nikki Zabel from Kapteyn Institute at the University of Groningen, but soon to be at the University of Cape Town, I believe. And she's going to speak about how cluster environments affect the molecular gas in galaxies. If you have questions, please put them in the chat, and we'll raise them afterwards. And now, Nikki, the floor is yours, if you want to share your screen.
Thank you very much. I'm very excited to talk about some of my stuff today. I'm also very happy to recognize lots of names. So it's been very lovely to meet some of you last week. So let me try and share my screen. And so today I'll be talking about basically my astronomical roots, which is molecular gas in dense environments, which is what my PhD was focused on and what I'm still very much involved in, even though I sort of made the transition to the dark side of H1 science. I understand that many of you don't really have an astronomy background, so I'm going to try and keep it relatively basic, but if it's too basic or if there is stuff that is still not clear, just feel free to interrupt me as well. I'm very bad at reading the chat while giving talks, so if you've got an urgent question, just like raise your hand or interrupt me or whatever. All right, so let's just start at the beginning with a very dry slide about galaxy clusters. So galaxy clusters are basically the largest gravitationally bound systems in the universe. They typically contain up to several hundreds to several thousands of galaxies. They're typically a few megaparsecs in size, and they have this very hot intracluster medium surrounding the galaxies. So this is basically an extremely hot plasma that sits between the galaxies and galaxy clusters, and that emits X-rays as well. So we can detect that from Earth here. You can see that very nicely in this image here. Yeah, that shows you the hot intracluster medium of this galaxy cluster. So to give you a little bit more of a better picture of what clusters look like, this is basically what I tend to think of when I imagine a galaxy cluster. So at the heart of the cluster, we have the brightest cluster galaxy, the BCG, which is typically a very large elliptical sitting at the center of the potential of the cluster, and that's surrounded by that hot intercluster medium that I mentioned, from which we get this X-ray light. Then we have all these satellite galaxies that fly on all kinds of different orbits around the BCG. They come in all kinds of shapes and sizes. And as you can see in this little video here, this creates this very, very turbulent, very chaotic environment. And as you can imagine, galaxies that live in galaxy clusters like this, they evolve a little bit differently. Their evolution is a little bit more complicated from galaxies that are more isolated, just because the environment they are in is so turbulent. And this is reflected in the sort of galaxy populations that we see in dense environments compared to less dense environments. So this is the famous morphology density relation, which was published among others by Dressler in 1980, which is where this figure is from. And I'm highlighting here spiral galaxies and elliptical galaxies. And what you see on the y-axis is the fraction of those populations. And on the x-axis, we've got the galaxy number density. So what you can see really nicely here is that the higher the number density of galaxies gets, the smaller your fraction of spiral galaxies gets, and the larger your fraction of elliptical galaxies gets, until eventually in very dense environments, elliptical galaxies outnumber the spiral galaxies. So that kind of suggests that galaxies in dense environment evolve in such a way that spiral galaxies are transformed into elliptical galaxies much more rapidly than we see for isolated galaxies. And there's a number of processes that happen in galaxy clusters that are thought to contribute to this transformation from spirals to ellipticals. So this is a really nice overview of the most important processes, a really nice cartoon by Ari Chung. If you are more involved in galaxy cluster research, you've probably seen this slide many, many times. So in the next couple of slides, I'll just highlight a few of the most important processes that happen in clusters that affect the quenching of star formations in cluster galaxies. So first of all, we've got starvation or strangulation. So the gas in cluster galaxies really sort of mixes and interacts with the intercluster medium. And so the galaxy loses some of its gas to the hot intercluster medium, and the inflow of new gas at the same time is prevented. So where normally in field galaxies, we have some circumgalactic medium, or we've got even some free floating neutral gas that can be accreted onto the galaxy. Because this galaxy is surrounded by this very dense plasma, this very hot plasma, that gas is not available for cluster galaxies. So as it continues to form stars, eventually it will just simply run out of fuel and the star formation will be quenched, and then we are left with a retired red elliptical galaxy as opposed to a spiral galaxy. So that's one of the ways in which this transformation can happen in galaxy clusters. Then we've also got something that is just the result of the sheer number density of galaxies and clusters, which is galaxy-galaxy interactions. So in the field, when two galaxies meet, they typically merge. That's one of the more important evolution scenarios for field galaxies, so galaxies that are not in clusters. But the velocities of galaxies in clusters are relatively so high compared to each other that instead of mergers, we usually get this very violent, very high-speed flybys instead. And that can really mix up the gas content, the gas distribution, but also the stellar distributions. And when such a flyby happens, you are just left with very, very asymmetric galaxies. And that can also really affect the star formation of these galaxies. And at the end of the day, quench the star formation and again, transform them into elliptical galaxies. And when these interactions happen to the same galaxy over and over again, we speak of harassment. And then there's another one that is the result of the presence of the hot intercluster medium, a mechanism that seems to be taking all the blame these days for the quenching of star formation in cluster galaxies, and that is ram pressure stripping. So as a galaxy moves through the hot intercluster medium, it really feels a very strong headwind from this hot plasma. And as a result, we can get that the material from the interstellar medium, so all kinds of gas phases, but also the dust and basically everything in the ISM can get really stripped away from the galaxy. And sometimes you can be left with these very spectacular tails that extend many kiloparsecs behind the galaxy. So this really removes the fuel for the star formation from the galaxy. And again, this can result in the quenching of the star formation and again, the transformation to an elliptical galaxy. So traditionally, as some of you will know very well, these environmental mechanisms have been traced very effectively by looking at the atomic gas reservoirs of galaxies. So atomic gas is typically distributed in very extended disks. It's relatively loosely bound, so it's basically an ideal tracer for these environmental mechanisms. It's really relatively easy to remove it from galaxies by all the means that I mentioned earlier. So these are some examples from the VIVA survey, which is a VLA survey of the Virgo cluster. And you can see really nicely in this bottom example here, the effects of ram pressure stripping on the atomic gas, where it's being removed from the disk on this side, and at the same time it's being compressed here on the other side. And in the top example here, we have a more general example of truncation, where you can see that the atomic gas disk is really, really small compared to what we typically see in normal field spirals. And that can basically be the end result of any sort of environmental mechanism, where you're just left with a very small atomic gas reservoir at the end of it. So that is very interesting and very useful. But at the end of the day, stars form in molecular clouds. If we want to really understand how the quenching of star formation happens and how the evolution of galaxies and cluster happens, we also have to look at the molecular gas. So the molecular gas is much more tightly bound and much more centrally located than the atomic gas. So you can see that nicely in this example here. It's the same galaxy as I showed before with the ram pressure stripped atomic gas. Now we can also see the optical contours of the galaxy here. And in the center here, we can see the molecular gas in these galaxies. So you can see that it's much more confined to the center, and there's just, it's just much less extended. So of course, it will be much more difficult for environmental processes to also remove this molecular gas from galaxies in the same way as it does for the atomic gas. So this is also why initially in studies of molecular gas in galaxy clusters, it's been very much debated whether molecular gas is also removed from galaxies in the same way. There have been some studies that have said that molecular gas content in cluster galaxies is very similar to that in fields, but more recently we have seen more examples of molecular gas also being affected by the same processes. So that is still a little bit, well, until recently that was still quite debated. And as I said, because the molecular gas is the direct fuel for star formation, it would have quite strong implications for galaxy evolution if it can also be directly removed by cluster environments from galaxies. So that's what I would like to talk more about today. So just for those of you who are not super familiar with studying molecular gas, I would like to just briefly explain how we detect molecular gas. So what we want to be ideally looking at is just H2 molecules, but because H2 molecules, as you can see in this cartoon here, are very symmetric, they don't have a permanent dipole moment, and so we cannot directly observe H2, unfortunately. So CO is the second most abundant molecule in the universe, and as you can see here, it does have a dipole moment, so we can more easily observe it through its rotational lines. So we typically use that as a proxy for H2. So that comes with all kinds of its own problems, because obviously we're going to need some factor to translate the amount of CO we detect to the amount of H2 associated with that, and that depends on all kinds of things like the metallicity of the galaxy, for example. So this is a source of uncertainty, but it's the best we can do, basically. So to study molecular gas in cluster environments, we basically did the ALMA Fornix Cluster survey, which is a complete survey of the 30 galaxies in the Fornix cluster that were previously detected with Herschel in the far infrared or in H1 with ATCA. And we do this sort of selection basically to ensure that there is some sort of interstellar medium present in the galaxies, because ALMA is very much a point and shoot kind of instrument. So we need to ensure that we expect to see some molecular gas in those galaxies. But that's the only selection criterion there was. So we didn't do any morphological selection or anything like that. So the survey has a bunch of different variety of galaxy types. So we've got some elliptical, some spiral galaxies, but also some dwarf galaxies in the sample. And then we observed in these galaxies the CO1 to 0 line with ALMA to create the first spatially resolved maps of the cold molecular gas distribution and kinematics. So I just wanted to briefly also tell you about the Fornix cluster. So the Fornix cluster is, together with the Virgo cluster, one of the two nearest clusters, or the clusters closest to us. They're both roughly at a distance of 20 megaparsecs, but traditionally it's been studied a little bit less than the Virgo cluster, partly because it is visible from the south, but a lot of very nice instruments are popping up in the south at the moment. So recently there's been a lot more studies of it in all kinds of different wavelengths. So that's very nice. As a cluster, it's actually quite different from the Virgo cluster, so it can also really teach us different things as well. So it's a lot smaller. The halo mass is roughly 10 to the 13 rather than the 10 to the 15 solar masses in the Virgo cluster. So it also has much fewer galaxies, but at the same time, the galaxy density in Fornax is much higher than in Virgo. So it's got about 2 to 3 times the number density of galaxies that Virgo has. So we also kind of expect different environmental processes to be dominant in both types of clusters for that reason. It's a lot more regular and dynamically evolved than the Virgo cluster. So Virgo has a lot of subgroups, infalling groups, and a lot of, it's basically really still forming. And Fornax is a lot more symmetric, a lot, just more evolved. It's only got one infalling subgroup that we know of. And because it's a bit of a smaller cluster, some studies even define it as a large group, really. It's probably a little bit more representative of the type of environment that most galaxies in the universe reside in, or at least the local universe. So this is a map of the Fornix cluster that is from the optical survey, the Fornix deep survey that came out a couple of years ago, which is a much very nice and deep survey, optical survey of the Fornix cluster. So that's all the black markers that you see. And then overlaid are the ALMA observations from our Fornax survey that are split up in non-detection, so galaxies where we don't detect any CO, those are the blue plus signs. And then galaxies where we do detect CO that looks very regular and undisturbed, and I'll show you an example of that in the next couple of slides. And then there are galaxies where we do detect CO that looks very disturbed and asymmetric, and those are the red triangles, and I'll also show you an example of that later. So basically we detected CO in half the galaxies that we observed, and more than half of the galaxies where we detect CO, the CO looks very disturbed. So we can already basically see that the molecular gas is indeed being affected by the cluster environment. And we also detected CO in a number of dwarf galaxies as well. So this is an example of the molecular gas in NGC 1387, which is basically a textbook example of what a very nice and normal looking molecular gas disk would look like. So on the left here, we've got the moment zero map, so the surface brightness distribution of the molecular gas. And you can see that it's basically just distributed in a very nice, very symmetric disk. And in the center, we've got the moment one map. So that is a velocity distribution of the molecular gas. And again, you can see it is a very nicely rotating disk, just very symmetric, just rotating perfectly normally, like we would expect in field galaxies that are undisturbed. On the right, I'm showing again the same moment zero map as on the left, but now it's overplotted as contours on an optical image, again from the Fornix deep survey. And that is just to show where the molecular gas is sitting compared to the stellar disk of the galaxy. So in reality, this is a very large galaxy. I'm only really highlighting the center of the galaxy here just to show where the CO is. But yeah, in reality, this is a very large galaxy. So the CO is really confined to the very center of the galaxy here. And this arrow here points into the projected direction of the cluster center. Now, this is an example of a galaxy with very disturbed molecular gas. So again, we've got the moment zero map here on the left. And as you can see, the gas is not really distributed in a disk. There are multiple blobs of gas and just lots of minima and maxima and just lots going on there. And the gas looks very, just very disturbed. If we look at the velocity map of this galaxy, we can see that also it's dynamically very disturbed, the gas. You cannot really detect any rotation here, but the motions are much more random than what we were seeing before. And then if we look where the gas is distributed compared to the stellar body of the galaxy, we can see that there is this really big blob of gas that is being stripped away from the galaxy towards the outside. And so we were wondering what is going on with this galaxy. Initially, just looking at the distribution of the gas compared to the stellar body, we thought it might be a case of ram pressure stripping, because you can see that the stars are really undisturbed. So if it was a tidal interaction, for example, you would really expect both the gas and the stars to be affected quite similarly, but because the stars are really just in the same place as before, basically, we thought it might be a case of just only the gas being stripped by ram pressure stripping. However, in sort of the classic cases of ram pressure stripping, if you've ever seen an example of that, what you usually see is that the velocity field is still very regular. It is just basically stretched on the side where the ram pressure is acting, but you can still very nicely see rotation usually. And that is not at all what we see here. We can see here that the motions of the gas are much more disturbed and much more random than that. So just based on these molecular gas observations alone, it is very difficult to say actually what is happening to this galaxy. It's a little bit mysterious. But yeah, at least we can say for sure that the cluster environment is also directly affecting the molecular gas in this galaxy, as well as the other gas phases. So this is to basically wrap it up all in one figure. These are the molecular gas fractions as a function of stellar mass compared to the field. So the gray areas that we can see here are the X-cold gas sample, which is a very large sample of the molecular gas in field galaxies. So this is the rolling median to that sample and the 1, 2, 3 sigma contours. And then all the colored markers are our molecular gas observations. So this has been, we've added some single dish observations from MOPRA, which basically mostly added some upper limits as well. And then I'm also splitting up the sample between galaxies with regular molecular gas that you can see in black here. So that's galaxies that look similar to the first example. And galaxies with disturbed molecular gas are highlighted in red. And galaxies with very, very strongly asymmetric molecular gas features are shown as red triangles here. So like the tail in the second example I showed. So there are basically two things that really stand out from this figure. One is that basically all galaxies that we observed in the Fornix cluster are deficient in molecular gas compared to the field. They're all consistently, with the exception of 1 or 2 galaxies, below the field median quite significantly. And then all galaxies with stellar masses below roughly 3 times 10 to the 9 solar masses have disturbed molecular gas. So basically galaxies with low stellar masses, it could be classified as dwarf galaxies, they all have disturbed molecular gas. So this is probably because of their smaller potential wells. It is easier for the molecular gas to be stripped from those galaxies. And we can also see that those are even more deficient in molecular gas compared to their higher stellar mass counterparts. So basically from this, we can say for sure that the molecular gas can be affected directly by the cluster environment, and it results in deficiencies and disturbed kinematics and morphologies as well. So that then kind of begs the question I mentioned earlier, that molecular gas is the direct fuel for star formation. So since we can see that these galaxies are very deficient in molecular gas and the molecular gas is very disturbed, what does this imply for the star formation in these galaxies? And to study that in more detail, we look at the Kanika-Schmidt relation. So the Kanika-Schmidt relation relates the star formation rate surface density to the surface density of the gas. So in our case, we're looking only at the molecular gas. And what this relation tells you is basically how efficiently the gas is forming stars. So if you have very high star formation rate surface densities for your gas surface densities, for example, you can see that this gas is very efficiently being transformed into stars. So from our ALMA observations, we get our CO observations from which we can estimate molecular gas surface densities. And then we collaborated with the Fornax 3D team, which is a mu survey of the Fornix cluster, to get H alpha measurements from which we can then estimate star formation rate surface densities to create the Kanika-Schmidt relation in the Fornix cluster. So this is basically the result. Both figures on the left and right are more or less showing the same thing, except that this one kind of highlights more the individual galaxies, and this is just all the resolution elements we've got in the Fornix cluster put together in the same figure. And we are comparing the relation we get for Fornax to the sort of classic relations from the literature. So the pink one is the one from Kanika 98, which is basically the Kanika-Schmidt relation. And then there's another one in blue, which is the one from Begil 2008, which is a little bit more comparable to what we are doing because they're also working with resolved observations and they're also looking at a variety of galaxy morphology types, whereas the relation by Kanika focuses more on spiral galaxies. So, oh, and then you can draw lines of constant depletion time. So depletion time is basically the opposite of star formation efficiency. So depletion time basically tells you if you continue to form stars at the rate you are doing today, how long will it take for you to run out of gas? How long does it take for the molecular gas to be depleted completely? And the typical depletion time for spiral galaxies in the field is roughly 1 to 2 gigayears, which is also reflected by those two relations from the literature. So what we can see here is that the Fornix cluster basically has depletion times quite close to both the field relationships that we can see here. There's a lot of scatter between galaxies. Oh, I didn't mean to click that there. towards both sides, but a lot more actually to the shorter depletion time size. There's only one galaxy here with significantly longer depletion times, but overall the sample is shifted towards slightly shorter depletion times than what we find in the relations by Kanika and Begil. So what that basically tells us is that the molecular gas in Fornax galaxies is still being transformed into stars very, very efficiently. So at least as efficient as in the field, and potentially a little bit more efficient as well, because we're looking at slightly shorter depletion times here. So this figure on the left is basically showing the exact same thing, but you can see a little bit more clearly where the different galaxies lie. So you can also see that there's very much scatter between the different galaxies. So they are spanning depletion times basically over 3 orders of magnitude. And you can also see that within galaxies, there's a lot of variation as well. So for example, this galaxy alone has regions inside that span also 2 to 3 different orders of magnitude. So there's a lot of variation in the Kanika-Schmidt relation between, but also within galaxies as well. So to look at that in a little bit more detail, we can plot the Kanika-Schmidt relation of individual galaxies, but we can also map the depletion times because it's just a ratio between the 2 axes. So if we divide both images by each other, we can also map the depletion times within each galaxy. So here I'm showing the same example as before, FCC 90, the galaxy with a very disturbed molecular gas. And if we look at its Kanika-Schmidt relation, we can see that the majority of the resolution elements lie towards very short depletion times. So they are much closer to 0.1 gigayears than the sort of usual 1 to 2 gigayears. But there's a lot of scatter within the galaxy as well towards longer depletion times too. So if we look at its depletion time map, we can see something that I find very interesting. And this is very sharp boundary between gas that is inside the stellar disk of the galaxy and the gas that is being stripped by the environment. So if you look at the gas inside the stellar disk of this galaxy, we can see that it has depletion times corresponding to 0.1 to 0.2 gigayears, which is very, very efficient compared to your usual field galaxy. But the gas that is being removed by environmental processes has depletion times that are longer than 10 gigayears or like 10, 20 gigayears. So the gas that is being removed from this galaxy is basically not really forming stars efficiently at all. So what we can see from this basically is that on average, the galaxies in Fornax are still forming stars quite efficiently. If you look at the total sort of Kanika-Schmidt relation, it's very close to that we find in field galaxies. But if we start looking in more detail at individual galaxies, we can see that the environment on more local scales can really affect what is happening to the star formation in individual galaxies as well. So the last thing I wanted to talk about in the Fornix cluster is molecular gas-dust ratios. Cosmic dust is basically particles of solid material that are floating around in the space between stars. So that can basically just vary from clumps of a few molecules to really large grains up to like several tens of millimeters. And dust is actually quite important for the star formation cycle. It catalyzes the formation of H2. So H2 molecules basically usually form on the surfaces of dust grains. And it also shields the molecular gas from radiation from outside. So it's quite important for protecting the molecular gas and making sure it actually has a chance to form into stars. So for that reason, we kind of expect the dust and the gas to be linked to some extent. And because we have seen that the molecular gas is being stripped from galaxies, we may expect the dust to be stripped in a similar way. And some people have studied this previously in the Virgo cluster as well, and they have found that indeed the dust can be removed by cluster environments from the centers of galaxies. So to look at this in the Fornix cluster, we're going to look at gas-to-dust ratios. Gas-to-dust ratios can tell you something about the chemical evolution of galaxies when you show it as a function of, for example, stellar mass, because it shows you kind of whether most of the metals are enlocked in the dust or in the gas instead. So these are gas-to-dust ratios in the Fornix cluster. So I'll just talk you through what is happening in this figure. So these are total gas-to-dust ratios. So the gas masses are the addition of the atomic and molecular gas over the dust mass. So we get the dust masses from Herschel observations. The Fornix cluster has been covered in all 5 wavelengths that are observed by Herschel. So we can make some SED fits to those Herschel observations to estimate the dust masses. And the atomic gas masses come from the APCA observations that were published in Loney et al. 21 that came out recently. And then again, we're comparing gas to dust ratios to a field sample. This time the field sample is Dustpedia, which is a very large sample of galaxies observed by Herschel. And that's because the way the dust masses were estimated and the molecular gas masses were estimated are basically identical between the Fornix cluster and this sample. So it's really to make a good comparison. The thing is this Dustpedia also covers the Virgo cluster. So I've split it up here between galaxies that are definitely in the field. Those are the gray markers, and galaxies that are within 2 virial radii of the Virgo cluster. Those are the yellow markers. And then galaxies within 1 virial radius of the Virgo cluster are highlighted with these larger markers here. And that's because all our Fornax observations are also basically within the virial radius, so that allows us to make a proper comparison basically between both clusters. And in the bottom panel, we just have the residuals of the cluster galaxies compared to the median to the Dustpedia field sample. So it's just to show a bit more clearly where the cluster galaxies are located compared to that median. So what we see here is that both in the Fornax and Virgo cluster, gas to dust ratios are suppressed. They are typically a little bit lower than what we see in the field galaxies, but that is not necessarily surprising because, as I mentioned earlier, the atomic gas is really easily stripped from cluster galaxies. So it's not really surprised that the total gas to dust ratios are lower than expected. So when we focus on the molecular gas to dust ratios alone, it becomes a little bit more interesting. So this is basically the same plot as before, but now just only molecular gas to dust ratios. And what we get now is that we get a split basically between both galaxy clusters. So in the Fornix cluster, we can see that molecular gas to dust ratios are still suppressed, not quite as much as the total gas to dust ratios, but still they are systematically lower than what we see in field galaxies. But in the Virgo cluster, we can see that molecular gas to dust ratios are more enhanced. So we basically get the opposite effect in both clusters, and that is a little strange. So possible explanations for the low molecular gas to dust ratios in the Fornix cluster, there's a couple of things that could explain that. So first of all, there could be a gas to dust gradient in the disk of the galaxy. So if your gas to dust ratios sort of increase radially outward in your gas disk, and then you start truncating this disk because of environmental effects, then you can be left with lower gas to dust ratios, lower integrated gas to dust ratios in the end. So I made a little toy model to basically test whether that could be the case. But it turns out that you need really steep gradients and really very severe truncation for this to explain the numbers that we see. So probably it does play a role, but it's not enough to explain the gas to dust ratios that we measure here. So another option is that dust could be replenished more efficiently by the star formation cycle than molecular gas. So it's been studied actually quite a bit whether supernovae are efficient at putting dust back into the interstellar medium, or if it destroys more dust than it puts back into the interstellar medium. And there are several studies that have found that supernovae are quite effective at putting dust back into the ISM, but they are not very good at putting molecular gas back into the ISM. So it could be that if you let the star formation cycle just carry on for a very long time, that eventually you will be left with more dust compared to molecular gas in galaxies. It could also be that the ISM in these galaxies is a little bit unexpected compared to what we are used to, and that we are not estimating the molecular gas masses or dust masses very well. So for example, it could be that there's a lot of CO dark gas. So as I mentioned earlier, we kind of have to guess how much H2 there is based on CO observations. And in some cases, there is molecular gas that is not actually traced very well by CO. So it could be that that is the case. Or it could be that the dust composition is different from what we are used to. So it could be that the dust grains have different sizes, or that the sort of elements we find in the dust are different from what we are putting in the models. So it could be for that reason that we are not estimating the dust masses perfectly. So these are all things that possibly play a role. What is a little bit more mysterious is the difference between the Fornax and Virgo clusters. So yeah, as I mentioned earlier, the Fornax and Virgo clusters are quite different places. So it could be that that plays a role. So Fornax is much more evolved and less dynamically active. So it could be that sort of in the earlier stages, such as the more sort of dynamically active Virgo cluster, there's an initial boost in molecular gas to dust ratios, after which it sort of calms down. Or it could be that things like ram pressure stripping, which we expect to be more important in Virgo because its halo mass is so much larger. It could be that that plays a role in changing gas to dust ratios in a different way than in Fornax. But really, we don't really know why it's so different between the two. Okay, that was all about the Fornix cluster. So before I wrap up, I just wanted to quickly introduce the VERTICO survey, the Virgo Environment Traced in CO. So Virgo is a recent ALMA ACA large program to really observe in a very uniform way the CO in the Virgo cluster. So the Virgo cluster has been studied a lot in the past, but there are a lot of different surveys at different resolutions, different sensitivities that are all kicking about. And the goal of the VERTICO survey was to really observe the CO in the Virgo cluster in a very homogeneous way. So it observed 51 spiral galaxies in the Virgo cluster. It was largely based on the VIVA sample, the VLA observations of the Virgo cluster. And the data paper for this came out in December last year, so have a look if you're interested in that. And this is sort of what the data looks like from VERTICO. So this is an overview plot of one of the galaxies, FCC 4402, which is also undergoing ram pressure stripping. So here we see the CO contours on a 3-color optical image from SDSS. And you can already see here really nicely that the molecular gas is also affected by the ram pressure stripping. It's a bit more disturbed on this side and a bit more compressed on the other side. And then we've got just our set of moment maps similar to what we had in the Fornix cluster. So that's sort of what the data for this survey looks like. And I wanted to briefly introduce a project that I'm working on for VERTICO, which is one of the first science projects that is going to come out soon, hopefully. And that is to study how the molecular gas, again, is affected in galaxies where we know which environmental processes are acting on them from the atomic gas data. So this is, again, very quickly the molecular gas fractions, same figure as I showed you before for Fornax, but now for the Virgo cluster, again, compared to the X-Gold gas survey. And we can see here that also in Virgo, the molecular gas fractions are slightly suppressed compared to what we see on average in the field. Also comparing it to the Heracles survey, Heracles is a survey of resolved molecular gas in nearby field galaxies. So this is really good for comparing resolved properties with field galaxies. But as you can see, Heracles has a little bit higher molecular gas masses, which is probably a selection effect that I will not go into the detail now. So as I said, what I was interested in with this project is to see how the molecular gas is affected based on the atomic gas properties that we know. So what this figure is showing is the molecular gas deficiency as a function of the atomic gas deficiency. So deficiency is basically the amount of gas that we observe compared to the amount of gas that we expect based on other properties of the galaxy. So for example, at a certain stellar mass, we expect to find a certain amount of atomic and molecular gas. And if that deviates, then we have got a deficiency in atomic of molecular gas. Sorry about that. So we don't have to worry about the different colored markers just now. But what this figure basically shows is that galaxies that are deficient in atomic gas are usually also deficient in molecular gas to some extent. However, there is not a significant correlation between the two. So even though galaxies are typically disturbed or deficient in both gas phases, the atomic gas deficiency is not really a good predictor of the exact molecular gas deficiency. The green numbers here highlight galaxies that are very famous cases of ram pressure stripping that have been studied a lot in the past. So these are also the galaxies that I'm showing some examples of on the sides here. So here the yellow contours are the atomic gas contours, and the red ones are the molecular gas contours. So you've got a bit of an idea of what both gas phases are doing. You can see in most cases that the molecular gas kind of follows the atomic gas here, so it's also being affected by ram pressure stripping. But what is interesting in this figure here is that it basically shows that galaxies that are actively undergoing ram pressure stripping are relatively rich in molecular gas compared to the rest of the VERTICO sample. So these are actually among the most molecular gas rich galaxies in the sample. So basically it shows that ram pressure stripping, at least when it's still ongoing and very much causing these asymmetries in the gas, it is not very good at removing molecular gas from cluster galaxies. And of course, a nice thing about ALMA is that you can resolve the molecular gas. So I just wanted to quickly highlight some of the resolve properties of these galaxies. So what this is showing is molecular gas radial profiles for the whole VERTICO sample, but grouped by their atomic gas deficiency. So the yellow line shows galaxies that are relatively H1 rich, and the most purple line shows galaxies that are very, very H1 poor. And again, the Heracles sample, so the comparison field sample, is shown as the sort of turquoisey dashed line. So what we can see very nicely is that galaxies that are very deficient in atomic gas have very truncated and very steep molecular gas radial profiles. So it looks like the centers of the galaxies are not really affected, but the really low surface density molecular gas from the outskirts is very much being affected compared to galaxies that are atomic gas rich. So this basically shows that whatever is removing the atomic gas from galaxies is very much also stripping the molecular galaxy or the molecular gas from the galaxies from the outside in. And this is shown basically in a different way in this figure on the left here, which shows the radius of the molecular gas disk as a function of atomic gas deficiency. And we can see here that there's a significant correlation between the two. So galaxies that are very deficient in H1 have more truncated, smaller molecular gas disks. So they're really, together with the molecular gas surface densities in the center kind of staying the same, that really suggests outside-in stripping of the molecular gas as well. So in the previous figure with the radial profiles, it looked like the molecular gas in the center was not really being affected, or at least maybe even being a little bit more elevated compared to H1 rich galaxies. There have also been previous studies in the Virgo cluster that have shown that the molecular gas in the very centers of galaxies is actually enhanced by ram pressure stripping and environmental processes compared to molecular gas in the outskirts. So basically to see whether that's the case also in the Fornix cluster, I'm showing here central molecular gas surface densities, again, as a function of atomic gas deficiency. So by central, I really mean the very center, so really the very central resolution element of the ALMA data. And while sort of by eye, it looks like there might be a correlation between the two, it turns out to not be significant. So basically here, there may be a hint of elevated surface densities in the center. We don't really find any evidence of increased molecular gas surface density in the centers of these galaxies. So that is all from me today. So I'll just quickly talk you through the conclusions we can draw from all this. So basically in the Fornix cluster, we have seen very much disturbed molecular gas morphologies and kinematics, suggesting that the dense molecular gas phase can indeed be directly affected by environmental processes. And we've also seen very strong molecular gas deficiencies that basically kind of confirm that. But despite these very strong disturbances and deficiencies, we can see that the star formation in the Fornix cluster is still very efficient. It's at least as efficient as in the field, and possibly in most galaxies even more efficient. We have seen suppressed gas to dust ratios or molecular gas to dust ratios in the Fornix cluster, but enhanced molecular gas to dust ratios in the Virgo cluster, which could be explained by a number of different things. And then when we looked at the Virgo cluster, we've seen that there is no strong correlation between atomic gas and molecular gas deficiencies. And we've seen that galaxies that are undergoing ram pressure stripping are actually rich in molecular gas compared to most of the other galaxies. And then we're looking at the resolved properties of galaxies in the Virgo cluster. We have seen that galaxies that are very strongly deficient in atomic gas have steeper and very truncated molecular gas radial profiles. So that suggests that molecular gas in these galaxies is also being removed from the outside in by environment. So while we can see that the molecular gas is definitely affected in those galaxies, the lack of a correlation between both deficiency parameters suggests that no significant amounts of molecular gas are removed in those systems. So that was all from me. Thank you very much, and I'll take any questions from there.
Thanks very much, Nikki. Do we have questions, folks? Raise hands, unmute yourself if you've got questions. Okay, while you formulate them, yeah, no, hang on. Patty has a question, of course. Patty, you want to go?
Hi, Nikki. Thanks for the great talk. Just a comment. It's quite interesting to see that you noted that in the Virgo cluster, there appears to be a more efficient sort of transformation from H1 to H2, because we see similar trends, for example, in galaxies in galaxy clusters like the Coma cluster, where there's copious amounts of H1, of H2, but not so much H1. Anyway, my question was this: what is the typical critical gas density required to form stars in these types of galaxies? And could this maybe explain the lack of efficient star formation activities in the tail because the H2 is so diffuse, fluffy?
Yeah, well, I have to admit, I really don't have a number for that from the top of my head. I really couldn't tell you, but I suspect that you are right, that the gas that is being removed somehow is just much more diffuse than the gas inside the stellar body. It's probably, yeah, probably very diffuse and not really in clouds. So that is probably why it's not really forming stars. Yeah, I agree.
Yeah, and just a follow-up question on that would be, what's preventing this gas from just disappearing into the ISM? Which is, I mean, I don't have the answer actually.
Yeah, it may just be time scales, to be honest, because that galaxy that I showed is a dwarf galaxy. So it could be that we're just catching it in a phase where, you know, the gas is sort of still attached to the galaxy, but it could just be that in the future it does sort of get merged with the ICM. Or it could be that it's still bound enough and it sort of returns to the galaxy. I couldn't really tell you. That will probably require some.
Okay, cool. Super interesting.
Yeah.
Thank you.
Right.
Cool. Anyone else? I've got an obvious parochial question. What can Meerkat contribute here?
Sorry, what was that? Sorry.
I've got a parochial question. What can Meerkat contribute?
Yeah, so of course there is the Meerkat survey of the Fornix cluster going on, and I think that will actually be very helpful, because from Alessandro's paper we have seen that there are, so he sort of also looked at whether galaxies have molecular gas or atomic gas and what is sort of the ratio between the two. And there were a lot of galaxies where they don't detect H1, but we do detect H2, which is maybe not that surprising. But there were also a lot of galaxies where we see the opposite as well. And it's basically just all over the place, which is very strange. And I think also in cases where we see this very disturbed morphologies of molecular gas, but we cannot really say why, because it doesn't look like stereotypical ram pressure stripping or tidal interaction or whatever. So I think if we've got these much more high resolution Meerkat data in the future, it will be much easier to pin down what exactly is going on and which processes we're actually looking at here. So very much looking forward to that data coming in. Yeah.
Cool. Any more questions? Paitsi, you still have your hand up. Is that for another question or?
Oh, sorry, I forgot to put my hand down.
All right. Anyone else? If not, well, we're just about at the top of the hour anyway, so let's thank Nikki again. Okay, thanks a lot, and we'll see you, most of you, at the group meeting next week then, or see you at the next colloquium. Okay, thanks, Nikki.
See you.
Bye, everyone.
Bye. Thank you. Bye.